Okay, section 7.2 deals with rational exponents. Now, before you get too concerned about this, the same properties that you already know, that you've already handled when we dealt with exponents, are the same properties you're going to use now. It's just instead of those exponents being integers, they're going to be rational numbers, meaning they're going to be fractions. So you're going to have to handle fractions rather than integers, but all of the properties are things that you already know. So the only new part is that there are rational exponents rather than integers. So let's take a look. A rational exponent is this idea that it's turning the radical into what we call a rational exponent. The nth root of a number can be expressed using radical notation or the exponent 1 over n. So I have an example here. Here we have the third root of 8. We're going to rewrite that as in exponential form, which means it becomes 8 raised to the 1/3. So here, the exponent becomes the numerator, and the index becomes the denominator. Just remember, this is the index. So we're just going to rewrite radicals as rational exponents. So the definition of a raised to the 1 over n, if n is a positive integer, then a raised to the 1 over n is equal to the nth root of a, provided that the nth root of a is a real number. So let's look at this. So this is the same as saying that 25 raised to the 1/2 is the same as the square root of 25. And that's all we're doing. We're just representing that radical as an exponent, but it's a rational exponent. So now we're going to write each radical expression using exponential notation. I'm not going to simplify these. I'm simply going to rewrite these. So this becomes 40 raised to the 1/3. Number 2 becomes 625 raised to the 1/5. 50 to the 1/2, and 27 raised to the 1/9. So you can see all I'm doing is taking that index, it becomes the denominator, and then the power on the number actually becomes the radical. Now I'm sure you can see for some of these some things that will happen. If I change, for example, this is called the base of the exponent, I can rewrite that as 5 to the 5th raised to the 1/5. You know what's going to happen here, but that's what's coming up in this lesson. A power to a power, multiplication, that answer just becomes 5. So let's take a look at now actually evaluating some of these rational exponents. We know that the square root of 4 is 2. When we look at this in rational exponential form, I can rewrite this as 2 squared to the 1/2. And then you can see a power to a power, that's going to simply become 2. The third root of -8 will be -2. The fourth root of 81 will become 3. And this one's tricky because the negative is not inside parentheses, so this actually is negative the square root of 9, which is 3. In radical form, this would actually be written as negative the square root of 9. And some of you might mistake that. It is not the square root of negative 9. Okay? That would look like negative 9 to the 1/2. So those are different. Depends on if it is included in parentheses or not included in the parentheses when you look at that. So now let's take a look at these rules. Like I said, you already know these, so it's not going to be anything new. It's just introducing the idea that they're rational exponents. So definition of a raised to the m over n. If m and n are positive integers and a to the 1 over n is real, then a to the m to the n becomes this power to a power. Power raised to a power. And of course, you know that that is multiplication. For example, if I have 81 to the 1/3, let's make that 1/4, 81 to the 1/4 to the 4th power becomes 81. Using radical notation, we can move between radical and rational exponential notation. In fact, the better you become at this, the easier it will be to do these problems effectively. Some notations work better on specific types of problems, so it's really going to benefit you to be able to move between these two different notations. So for example, if I say I have 5 to the 2/3, you should be able to write that as 3 root 5 squared pretty easily, moving between those two different types of notations. Evaluating a raised to the m over n, if m and n are positive integers and a raised to the 1 over n is a real number, then what you can do is use this in simplifying some of these expressions. So you can actually take a radical or a rational exponent and simplify it this way. You might have something like 27 to the 2/3, for example. So if I rewrite that as 27 to the 1/3 squared, it becomes a lot easier to understand because 27 to the 1/3 is 3. 3 squared is 9. So that's how we're going to use this idea of moving between these notations a little differently. You could also use the radical notation, which would have you use this idea of 3 square root of 27 squared. If you did that, you could actually become 3, or the 3rd root of 3 raised to the 6th power, which would be 3 squared, which would give you 9, as you're simplifying that. Again, definition of a raised to the m over n. You've seen this before. Before we saw that when we had a raised to the negative n, it became 1 over a to the n. This is the same rule, only now it's a rational exponent. So as soon as you put a to the m over n in the denominator, it becomes positive. Using radical notation, you're just going to rewrite that as 1 over that nth root of a to the m. And you can write this as the nth root of a to the m, or as the nth root of a to the m. They are equivalent. So either one of those notations is correct. So let's take a look at writing each radical expression using exponential notation. So this becomes x to the 2/3. Remember, the index is in the denominator and the power is in the numerator. So now, when I have 1 over the 4th root of m to the 3rd, that would become 1 over m to the 3/4, and you could write that as m to the negative 3/4. Please keep in mind we don't want negative exponents in answers on our tests or on any of our homework. We want to get rid of those. That's just an example to show you how you would rewrite that. Number 3, the 4th root of 9 squared could be rewritten as 9 to the 2/4. Remember, you can reduce these rational exponents, so that becomes 9 to the 1/2, and you know that that becomes the square root of 9. Both of these will give you 3. Number 4, the 3rd root of b to the 4th becomes b to the 4 over 3. Remember, the index is what goes in the denominator. Recall the rules for exponents. As I said, you already know these. When you have like bases, you are multiplying like bases, you add the exponents. When you are dividing like bases, you subtract the exponents. When you are raising a base to a power, you multiply the exponents. Also, when we have bases that aren't alike, when we have the product of bases raised to a power, that's the same as raising each base to the power and then multiplying. So the product of the bases to a power is the same as the product of the bases, the powers of the bases to the product. And also, the last one, number 5, when I have two different bases raised to a power, I can rewrite that as each base raised to that power separately, and I can move back and forth between these two representations depending on what my problem looks like. Let's take a look at a few problems using the product and quotient rules for rational exponents. So here, I actually have like bases. I can do a couple of things. If I recognize that I have, this is, well, actually, let's just leave those bases alone for now. We'll just go straight with the rule. 27 to the 1/6 plus 1/2. I have like bases. I'm going to add those exponents. So that means I have 27 to the 1/6 plus 3/6, which gives me 27 to the 4/6, which is 27 to the 2/3. And some of you might recognize that 27 is actually 3 to the 3rd. You can rewrite that as 3 to the 3rd raised to the 2/3, and that would be the product rule, power to a power, so 3 times 2/3 is going to give you a 2, so that actually becomes 3 squared, or 9. So that is actually both the product rule and the power rule in one problem. Number 2, I have like bases. I'm dividing, so this time it becomes 5 to the 3/4 minus 1/4. That becomes 5 to the 2/4. I can reduce that, and it is 5 to the 1/2. In radical notation, that's the square root of 5. So the idea is that you practice a lot of this so that you can move back and forth very easily between the notations and become very, very familiar with these types of problems. Next, I have 3 to the 1/2 times 12 to the 1/2. So now my bases are not alike, but I can rewrite this as the product of the bases raised to the power. So that's going to give me 36 to the 1/2. You might see very easily that that is 6, or you can rewrite it as the square root of 36, which you know is 6. Makes it a lot easier to see. Number 4, I have a power to a power. So 3 to the 10th times 1/2 is going to give me 3 to the 5th. Number 5, now I have the quotient raised to a power. So I can rewrite that as 2 to the 6th to the negative 1/3. And 3 to the 9th. To the negative 1/3. Now remember, we're also dealing with a negative exponent here. Where you choose to turn that positive is up to you. You could do it at the very beginning. Remember, a to the negative n becomes 1 over a to the n. So we could flip this upside down and make it 3/9 to the 2/6 raised to the 1/3 power. And continue from there. You can do it at this point, or you can wait and do it at the end. So here I would have then 2 to the negative 6/3 and 3 to the negative 9/3. That's going to give me 2 to the negative 2 over 3 to the negative 3. That becomes 3 to the 3rd over 2 squared. And you might see that you have that also if you decided to eliminate the negative in the beginning. So 3 to the 9/3 over 2 to the 6/3 is going to give you 3 to the 3rd over 2 squared. Oh, okay, here we go. So now we're going to look at the square root of x squared. When we look at this, there's one little thing we have to add when we're looking at this. So when simplifying expressions involving rational exponents and variables, make sure to write equivalent expressions. So if I have x squared to the 1/2 equals x, that looks like a correct application of the power rule. However, if I have negative 3 squared to the 1/2, then I get 9 to the 1/2, which is 3, which is clearly not a true statement. So what I have to do is I have to add absolute value symbols to ensure that what I started with was positive. So when I'm looking at this, we're going to see this, and we'll talk more about this in class, I'm sure, because it can be just a little bit confusing when we're looking at this. So if I'm looking at simplifying each of these expressions, I have x to the 8th and x to the 4th. Let me see so I get to the right place. Okay, so when I'm looking at this, and I have x to the 8 over 4 and y to the 4 over 4. That's going to give me x squared y to the first power. This is one of those that when you look at this, you have to ask the question, are they equivalent? Or what will make them equivalent? If you look in here, y will be positive. But out here, you're not assured that y will be positive. So in order to make them equivalent, you must put those absolute value symbols around the y. Okay, number 2, x to the 9/3 over 8 to the 1/3. That's going to give you x to the 3rd over 2 to the 3rd to the 1/3. So x to the 3rd over 2 will be your answer for number 2. Next one, simplify the following expressions. I have like bases, so remember, when multiplying like bases, you add the exponents. So that's going to give me x to the 6/3, which is x squared. A, dividing like bases, you're going to subtract, so a to the 1/2 minus 1/4 is going to give you a to the 1/4. Number 3, raising a power to a power is multiplication. So now I have x to the 1/2 times 1/2, y to the -3 times 1/2. It's going to give me x to the 1/4, y to the -3/2. Number 4, I have x to the -1/2. I actually think I'm going to eliminate that negative right away. I think it's easier to handle it that way. So I'm going to have y to the 1/3 over x squared raised to the 1/2. Power to a power gives me y to the 1/3 times 1/2 over x squared times 1/2. That's going to give me y to the 1/6 over x. Now again, this is one of those cases where I started with x squared. So x is ensured to be positive here. Down here, I have x to the 1st. I have to guarantee that that will be true, so I have to put absolute value symbols around that to ensure that it would be positive. Okay, true or false, can we say that 9 to the 1/3 is the 3rd root of 9? The answer is true. Number 2, 8 raised to the 5/3 is the 5th root of 8 to the 3rd. That is false. Remember, the index is in the denominator. Index is in the denominator. Number 3, 6 raised to the 1/2 is equal to the square root of 6 over 6, and that is true. We haven't talked about rationalizing the denominator yet. But if you think about this, this becomes 1 over the square root of 6. Rationalizing the denominator, we're going to multiply numerator and denominator by root 6. So we'll have root 6 over the square root of 36, which is 6. And we'll do more of that in another section. Now I have 2 divided by 2 to the 1/2, and that's going to become 2 to the 1/2, and that is true. We're subtracting 1 minus 1/2. Number 5, 16 raised to the -1/4 is negative. True. Oh, don't be fooled. That is false. This 16 raised to the -1/4 becomes 1 over 16 to the 1/4, which would become 1/2. Number 6, 6 to the 1/6 times 6 to the 1/6 is going to be 6. Remember, you're adding exponents, so 2 to the 6th which becomes 6 to the 1/3. So that is true. There's your homework. I'll see you tomorrow in class. Have a good evening.